All right. Well, let's get to it then. So COVID-19 is all testing is all over the news. Are we testing enough? Who should get tested? What type of test should we be using? And I'm not actually really going to talk about any of that. This is a good follow-up to the first presentation. I'm going to be talking about testing errors. I'm going to be talking about the FDA's emergency use authorization. So there's been an emergency use authorization for COVID-19 diagnostic testing since February 4th of this year. If you want to do any research on these tests, you can go to the FDA's website. You can comb through the tests they list there and then open up a PDF document that the manufacturer has submitted to the FDA to try and pull out whatever information you need. That's pretty tedious, so we built an application at In-Q-Tel to help do that research. I'll be talking a bit about that. But first, let's back up just a little bit. We'll start with a primer on COVID-19 diagnostic testing. If you're like me from a few months ago, you could probably use that. Then we'll talk about why tests fail, where do these errors come from, and then we'll get into the application that we built. So there's three major types of coronavirus diagnostic tests. The first and most common is the molecular PCR test. That's the one where they take the Q-tip and jam it way up your nose and drop it in a test tube and ship it off to a lab. PCR tests measure the presence of the virus directly by detecting viral RNA. What that means is that in theory, it should be impossible to get a false positive with a PCR test, but in practice, we actually see that there are false positives with them as well. The next two types are antibody and antigen tests. So antigen is a substance that your body creates to induce an immune reaction in the presence of an infection. And an antibody is that immune reaction to the infection. And so both of these tests measure the presence of coronavirus indirectly. They're measuring your body's response to the presence of an infection. And that makes them a little noisier than the PCR test because every body is different. That's not to say that the technology is inherently inaccurate. We use these sorts of testing technologies for lots of diseases, just that the process is a little bit less direct. You can use PCR tests and antigen tests to diagnose a current infection. Current CDC guidance states that you should not use antibody tests to diagnose coronavirus infection, but you can use them to diagnose a recent past infection of coronavirus. The PCR test is generally you can detect the presence of the disease soonest because it can take your body days or weeks to ramp up its response to the presence of the infection. So in a clinical setting, we might want to ask two questions that we can hope a diagnostic test can answer. Does the person tested have the disease, or can we rule out the person having the disease? To answer the first question, we need a high positive predictive value, meaning that a positive test result means it is likely that you have the disease. To answer the second, we need a high negative predictive value, meaning a negative result likely means you don't have the disease. And unfortunately, a test can be good at one and not so good at the other, or there's a bit of a trade-off between the two. A third question about population surveillance and the prevalence of the disease in the population is important and interesting, but a bit out of scope. So I'm just going to leave it there and move on. Tests can give you false diagnoses for several reasons. I'll go through these in turn. So this is a bit of an eye chart, but what it's showing is the likelihood of detection from different testing technology across the cycle of an infection. The bottom line is that a test can give you false negatives if you test too early and the substance that you're trying to detect is too low, or if you test too late and the substance you're trying to detect has decreased within the person's body. Or sample collection can also be a source of false negatives. There may not be enough of the substance in blood, saliva, or on the end of that Q-tip. And PCR tests in practice tend to be more vulnerable to this because just the nature of the sample collection, it's very uncomfortable for everyone involved, and it can be hard to get a good sample. And then cross-contamination is a source of false positives. And so that's where in the PCR test, we do see that in practice. Individual samples can get mishandled and come back positive, or equipment can become contaminated and whole batches of samples will all test positive. So getting into the statistics, I think the first presenter covered these pretty well. Um, so here's what I'll say, just to emphasize it. Sensitivity and specificity are calculated by the manufacturer when they do an experiment to submit to the FDA for EUA approval. Those are characteristics of the test. But what we really care about from the question slide is positive predictive value and negative predictive value. And those are a function of both the characteristics of the test interacting with the prevalence of the disease and the population being tested. So in practice, we often don't know what this is for any diagnostic test. And our testing strategy actually, who we decide to test and under what circumstances can change that. That's a pretty mind-bending result. I'm not going to throw math at you and rehash Bayes' rule, but I'd like to give you some intuition. So looking at this chart on the left, we have disease prevalence or the infection rate along the x-axis, PPV along the y-axis. Ignore the shaded region for now, we'll get to that, but that solid line is how PPV changes as the disease prevalence increases, holding the test constant. And so what we see is a few things. One, PPV is an increasing function of disease prevalence or the infection rate. And two, when the disease is rare, PPV is actually lower than we would like, meaning the risk of a false positive is pretty high. And so that might be true, aggregating across a whole population being tested, but you might be thinking, well, if I as an individual want to get tested, what does the infection rate of the population have to do with me? And really what that means is that we're using the infection rate as a proxy for prior probability of infection. So consider two examples. I don't have any symptoms. I don't have any known contacts that are infected. I don't engage in risky behavior. I get a positive test result. What that means is don't panic. There is a substantial chance it's a false positive. That's okay. That doesn't mean the testing system is broken. What you need to do is be careful and then go get retested, hopefully at a different center or with different technology to try and keep the errors independent. Two positive tests, you're almost surely infected. The other scenario, though, is even if I'm in an area with a low infection rate, if I'm showing symptoms, if I'm engaging in risky behavior, if I have known contacts, I'm moving right on that chart. So my individual prior probability is high. If I get a positive result, you can trust that. Ditto for, there's a similar logic for the negative predictive value, except it's reversed. High prevalence or higher prior probability makes it more likely to get false negatives. So going back to this FDA website, you want to say you're a public health official, you want to purchase a test, you want to make sure that it's compatible with equipment that you own, you want to make sure it's available and it's accurate, but it's tedious to browse the PDFs. So we made an application. Here's one view. Here's another to help you do that research. And so you do a quick demo. All right, so here we see the database tool. You can sort on any one of these columns. We have links to the website of the manufacturer, the FDA EUA documentation. You can filter on things like the equipment used for sampling or the instrument or platform you need to use to see what's compatible. You can click on the row. It brings up contact information and other metadata that we've pulled out of those PDF documents. And then you can click on this performance link here, and it will take you to the other part of our tool. So now this should look familiar. This shaded region is a 95% confidence interval, where we took the data that the manufacturer reported, got the 95% confidence interval in sensitivity and specificity, carried it forward through the calculation. You can select one of about 160 different tests we have performance data for, but this is pre-selected because I came through the database link here. On the left is that PPV chart for my coronavirus test. On the right, we've placed PPV for a rapid diagnostic for influenza. We did this because we wanted to provide a baseline. How well does this coronavirus test behave compared to a test that we use for a common disease that's in common use now? You can see the shape of the curves are the same. So the confidence interval is a lot narrower on the flu test because it was done, there was a much bigger clinical trial done to validate its efficacy. We've got the same for the negative result here. And then if you scroll down below, for those that aren't good at math or don't like math, don't want to stare at a chart, in plain English, we've got, if you were to give 100,000 of these tests, what percentage would you expect to come back positive, negative, et cetera, et cetera. And you can change that by modifying the slider here. And then it'll update the language and the chart itself. And the last thing for the demo is that you can download the data that we collected that backs up these charts if you want to do your own analysis. All right. So bringing us home, many of the manufacturers don't report a lot of really good data. You'll see a lot of charts like these, big confidence intervals, 100% perfect classification in that experiment. My read on these would be to just say we don't have enough data to say how well this test will be performing in the real world. It could be good, it could be bad. We just don't know from what's been reported. We focused on molecular PCR tests, although antigen tests are shortly to follow. We're not so sure about antibody, but open to that discussion. And again, just emphasizing, the data that the manufacturers report may not relate to the real world. So this can give you an idea of how it performs, but don't have an illusion of precision. Still under active development, here's our roadmap. This was a big cross-domain effort with all the folks at In-Q-Tel across 3 different business units, including computer scientists, statisticians, biologists, medical doctors, epidemiologists. Here are some links. I can drop them into the chat window to go see the tool. You can email us, covidtestdb@bnext.org, for questions, comments, or if you want to get involved. And this is open source on GitHub under active development. So feel free to send us a pull request or open up an issue. That's all I've got. Thank you.